The Roque de los Muchachos, on the island of La Palma. The extinct volcano is some 2,400 meters above the sea. Just below the edge of the crater, two exciting modern instruments have been installed: the MAGIC telescopes. Using these telescopes, distant objects can be observed way beyond the known universe of planets, stars, and galaxies. Some of them emit in a short time more energy than our Sun over its lifetime. Part of it comes as very highly energetic electromagnetic radiation, the so-called gamma rays, to which MAGIC is sensitive.
With these two telescopes, we obtain access to a part of electromagnetic spectrum that could not be observed so far. We can observe active galactic nuclei, supernova remnants, neutron stars, and black holes. Our observations will also contribute to better understanding gamma ray burst and the mysterious dark matter.
MAGIC is short for Major Atmospheric Gamma Ray Imaging Cherenkov. The telescopes were designed and constructed by an international collaboration, which also ensures their operation and the analysis of the data. The biggest contributions come from institutes in Germany, Italy, Spain, and Switzerland. More participating groups are in Bulgaria, Croatia, Finland, Poland, and the USA. The telescopes cannot observe gamma rays directly. They record faint bluish flashes coming from high layers of the atmosphere called Cherenkov radiation. This radiation arises in the atmosphere during the absorption process of highly energetic gamma rays from the universe. A gamma ray colliding with an atomic nucleus in 5 to 20 kilometers altitude diffuses into neutrons of ever lower energy. They fly through the atmosphere as a tightly collimated bundle, and together radiate a short flash of visible light formed like a thin disk. This faint light can be recorded by suitable telescopes like MAGIC. Cherenkov flashes are very faint indeed. To see them, even with very sensitive instruments, a clear sky and as complete darkness as possible are needed. Those criteria make La Palma an optimal site for MAGIC. The top of the Roque de los Muchachos is very rarely shrouded in clouds, and light pollution at night is minimal, also because of local lighting restrictions imposed by law. This has brought many other international telescopes to the Roque, most of them optical. Even so, for observations with MAGIC, only nights with no or very little moon are suitable. The two MAGIC telescopes have the largest reflecting mirrors of any existing gamma ray telescope. Each reflector has a diameter of 17 meters. The reflector is carried by a support frame more than 4 meters deep, made of lightweight but very stable tubes of an epoxy resin and carbon fiber composite. The mirror surface of 234 square meters is tessellated. In MAGIC 1, nearly 1,000 individual mirror elements of 50 by 50 centimeters. Each element has a diamond-milled aluminium surface with a quartz coating to protect from atmospheric corrosion. 4 elements are fixed on a movable panel. MAGIC 2 has movable elements of a square meter. The mirrors are moved to give an overall mirror shape of a parabola. Refocusing is done permanently under computer control. The camera is constructed like a modern digital camera of individual light sensors, although they are particularly sensitive. In MAGIC 1, they form a hexagonal matrix of 576 light sensors, so-called photomultipliers.
Utmost sensitivity of the sensor and efficiency of the light collection are critical elements of gamma ray telescope. The photomultiplier are capable of reaching even to a single photon. They transform the faint light flashes into electrical signal, which get amplified and transmitted. The signal lasts only 100 millionths of a second.
To avoid drowning the Cherenkov signal in the unavoidable light of the night sky, the exposure time has to be very short. This requires very fast electronics, capable of following the signal in steps of a billionth of a second. Some remaining background can be eliminated by statistical methods, which requires long observation time if the signal is weak. Apart from the observation direction, also the precise absolute time of each shower is recorded. Using this information and the brightness of the shower, gamma rays can be reconstructed. Multiple showers permit defining the flux and energy spectrum of a source. The design and construction of the MAGIC telescopes was a major technological challenge, but it was rewarded. The MAGIC telescopes are now able to observe gamma rays in an energy domain that so far was not accessible to satellite-borne instruments and previous generation telescopes. Their light weight also permits observing the short-lived gamma ray bursts. These enigmatic events were discovered some 30 years ago, and thousands of them have been observed since then. Their origin is still largely a subject of speculation. The mirror dish of the MAGIC telescopes can be directed to any point in the sky in less than 50 seconds. The occurrence of gamma ray bursts is signaled by large angle detectors on satellites.
On July 13, 2005, a satellite detector was observing a gamma ray burst and was broadcasting its position in the sky. So we did react immediately to that alert, and we positioned our telescope in the source in the sky. That was for the first time that a gamma ray burst was observed during the prompt emission from ground at a very high energy regime. That was very important, I think.
In this observation, MAGIC did not detect any gamma rays. In this energy range, the gamma ray bursts so far have kept their secret. Routine observations with MAGIC 1 started in early 2004. Placed next to it, MAGIC 2 started operation in early 2009. Showers can now be observed by the telescope tandem, using the stereo effect to more than double the system's sensitivity and precision. The increased sensitivity AGNs often develop two jets in opposite directions. Through them, matter is expelled into the intergalactic space. If a jet points roughly in the direction of the Earth, high-energy particles, including gamma rays, can be observed. Such active galactic nuclei are called blazars. Gamma radiation from a blazar provides important information about jet composition and acceleration mechanisms. This permits modeling the conversion of gravitational and rotational energy near the black hole into radiation.
MAGIC has so far observed 7 known active galactic nuclei and has discovered 6 new ones. The 2 most newly discovered are the ones most distant from us ever to be detected in very high-energy gamma rays. The most distant one is more than 5 billion light years away from us.
The universe is a fascinating field of research, still full of unanswered questions. Scientists are struggling to find categories for the objects they observe. Apart from galaxies, stars or planets, the universe also harbors many strange objects. For instance, pulsars. Pulsars are rotating neutron stars, extremely dense remnants of stars that burnt out and collapsed. A typical pulsar has a radius of only 10 kilometers, but a mass comparable to that of our Sun. Some pulsars rotate tens, even hundreds of times per second around their axis, generating high magnetic fields in their vicinity. The fast rotation and the high magnetic fields cause a pulsed electromagnetic radiation at different wavelengths, also in gamma rays. The MAGIC telescopes can study how far in energy the pulsed radiation can reach. In May 2008, MAGIC succeeded in showing for the first time that the gamma radiation of the Crab Nebula also contains a pulsed component. MAGIC may also help to understand one of the great riddles of modern physics. In fact, only a small percentage of the universe can be observed directly. Most of it is called dark matter and dark energy, and can be inferred by its gravitational effects on stars and galaxies. Scientists assume that this dark matter is not made up of the same constituents as all matter we know, but of particles unknown so far. Theories predict that in collisions between such particles also gamma rays can be produced, with some small probability. To identify such collisions in observations by MAGIC would be a major discovery in cosmology. In a collision of galaxy clusters, the dark matter can become separated from the normal matter. This effect has been determined by evaluating how the cluster distorts light emitted by more distant galaxies. In this image, scientists show dark matter in false blue. Red hot gas and yellow or white galaxies indicate normal matter. Many more open questions exist around the origin of the universe. Already exploring electromagnetic spectra of various sources is a tedious puzzle. Cosmic sources are observed in very different wavelengths. In gamma rays and X-rays, in ultraviolet, visible and infrared light, and down to microwaves and radio waves. Each new observation is based on the dedicated work and on new ideas of a team of scientists, and contributes a piece to the puzzle. Together, they will eventually succeed to see the universe in a new light.
Apart from being hit by the gamma radiation of the individual sources, the Earth's atmosphere is also continuously being bombarded by high energetic particles, the so-called cosmic rays. These cosmic rays have been studied for several decades by now, but the origin has not been fully understood yet. The main reason is that the cosmic rays mainly consist of charged particles which got deflected on their way to Earth by extragalactic and galactic magnetic fields. This makes it very difficult to pin down their origin in contrast to the gamma rays.
Supernova remnants in our galaxy have long been considered possible sources of gamma rays. MAGIC has been able to show that this is true for some objects.
MAGIC has detected two supernova remnants, IC 443 and Cassiopeia A. In a supernova, a dying star ejects up to 90% of its mass in its surrounding medium, forming shock waves. In these shock waves, particles are accelerated, and those particles are what we observe here on Earth as cosmic rays. In addition, in supernova remnants, also very high energies gamma rays are produced, which we detect with MAGIC. And